What we're going to look at now is a couple of conventions that are used when talking about logarithms. So the first one is going to be what's called the common logarithm. And so this is typically used, used for a base 10 logarithm. So it sort of follows along the lines of how we would usually write, like, instead of writing a 2 above a root x, we just sort of assume that if there's no 2 written there, then it is the square root, as opposed to like cube roots, fourth roots, etc. So the default is 2. And so that's going to be the same with logarithms. If there's no base written, the default is this common logarithm base 10. So you probably won't see base 10 logarithms much anymore because they're going to be replaced with just this log notation. I've got here an application that really commonly uses this log function, and it's the magnitude of an earthquake at a Richter scale. Basically, the Richter scale is evaluated by taking a base 10 logarithm of a particular intensity measure of an earthquake. So that's basically a measure of power, essentially. And so we just have this formula here, R equals log of however that intensity is measured. So I'm not going to give you units or anything because it gets a little messy at that point. But yeah, I'll just give you the I. So for the first question, it's going to be pretty straightforward. Find the magnitude of an earthquake with I equals 4.3 times 10 to the 7. So then essentially what we're doing is just plugging that I into the formula. So I'll have R equals log of 4.3 times 10 to the 7. We'll have ways to clean that up a little bit better later, but for now, I'm just going to plug in that 4.3 times 10 to the 7. Remember, that's scientific notation. So that just means, like, you can multiply it in your calculator if you like, but that should mean that decimal has 7 things after it. Sorry, we move the decimal 7 places to the right, and that's where the new decimal goes, so 7 spaces. So if I move that over, I will get 4, 3, and so it's going to 1, 2, 3, 4, 5, 6, 7. So that is going to be our new number. So that's where the decimal would go, and it's just zeros after the decimal. So that should be 43 million, I think. Yeah. And so I can just plug that in the calculator, log of 43 and then 6 zeros. And so remember, I did mention this in one of the other videos, but how we would plug that in, there's typically a button for your calculator here. So there should be a button that says LOG on it. And then just type in that number, 43 million, and hit equals. And so I'm getting a 7.63, let's say. So that would be our measure on the Richter scale. So I mentioned before, logs are very, very slow growing functions. So they have a tendency to take this huge number, 43 million, and turn it into like a very manageable number, 7.63. And so to get a feel for what logarithms actually do here and why we use this scale, so the second question is, if the magnitude increases by 1, how much stronger is the earthquake? So I think what we can do is actually maybe let's look for a pattern here. There's a mathematical way to do it, but we haven't gotten quite there yet. So let's see what happens if I set up a table. So I'm going to have my magnitudes of R on the left. So let's say we start with like 1, 2, 3, 4, 5, 6 and see what happens. And then what I need to do is get my I from that. And so we'll have to do a bit of a calculation there, but we can figure that out. So if you recall, if R equals log I, that's the exact same thing. Remember, so that log is a base 10. So we can flip that over to the exponential version of the equation by swapping the input for the output. So instead of having an output of R, it's going to be the input for the exponential. And then that input of I in the logarithm becomes the output of the exponential. And so I can use that to figure out all of these i's. And so what I have here is this would be 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. I'll write out the first couple of these, but hopefully you get the idea. It's 100, 1,000, 10,000. Then we should have, I'm going to start putting commas in so I can keep track of these, 100,000 and a million. And so what we can actually see taking place here is that as R goes up by 1, then I, so it doesn't go up by a constant amount, I gets multiplied by 10. So addition of 1 on the Richter scale actually means a power or intensity magnitude increase of 10-fold, so multiplied by 10. So then it's 10 times stronger. So it actually kind of converts you back and forth between like a linear scale and an exponential scale. Yeah, so that's sort of that's the idea behind your Richter scale. That's how that works. Another scale that works very similar to this is decibels, so a measure of sound. Yeah, so it's gonna be the same idea. It's a similar formula. It's just a different intensity measure, and just the idea being that when really big things are already happening, it takes a much bigger increase for you to notice a change than when not much is happening. So like as far as an earthquake going, I used to teach outside of a busy street in Vancouver, and like the example that I would give is, let's say every student is writing a test and a truck goes by on the busy street, like it's so quiet in the room and this truck goes by, you're going to notice that truck, right? On the other hand, if there's already an earthquake happening and then that truck drives by, you are not going to notice that truck. So you need like a much bigger intensity to be added to that situation for you to notice it. So that's kind of what logarithms do for us. So that's one example. The other type of logarithm that I want to talk about is the base E logarithm. Wait, so for the base E logarithm, we also have a notation for that one. So we would write, instead of log base E of x, you're going to see this ln of x. There's no particular reason why it's written inscriptive there. It's just something I always do. I don't know why, but yeah, I'll always write that ln combined like that. And we usually read it as lawn, like L-A-W-N, like your front lawn. That's how it'll typically be read out. So yeah, we have this ln of x. It's called the natural logarithm. So I guess sort of the ln comes from backwards NL, I don't know. And it might seem pretty unnatural because it relies on this like horrible number e that I described before. But again, when you see this in calculus, you might maybe understand a little bit more why it's considered natural. Things just work better with it, essentially. So just a few examples to go through here. There will be lots and lots of applications with the log base e because most applications will actually use base e exponentials. I just don't want to get into them yet because they take a little bit of explaining, and there's a whole section for that later. So for the first one, ln e cubed. So for this one, we can actually just go ahead and do cancellation because ln is the inverse of the e exponential. So for that one, we should be able to just write 3. For ln of 53, so this 53 is probably not a perfect power of that 2.7 ... number. So for this one, I'm going to use a calculator. And right beside your log button, you should probably be able to find a ln button. And so you just hit that button, and it should do this calculation for you. So if I punch this in, ln of 53, I should get 3.97. And yeah, so finally, we can also use this to solve some really basic equations at this point. We're going to solve e to the x is 3200. So to solve equations, I can think of this as two ways. I could use that sort of conversion formula to go from exponential to logarithms, but another justification of that formula is that we apply inverses to solve for x. So the thing happening to x on the left here is an exponential with e. I can cancel that with a ln on the left, and anything I do to the left side, I have to also do to the right side. And so those are going to cancel for me. So I'll do that in the same color I did it before so you can see what's what. So those are going to cancel, and then the left side is x equals ln of 3200. This is the exact equation that you would have gotten from that like equation reconstruction formula I had shown you before. So we get x is ln 3200, and I just punch that in the calculator, and I get 8.07. I use a little squiggly equals there, and I should have technically used one here because there was rounding error. I don't expect you to use that squiggly equals, but do pay attention when I ask, especially on WebWork, for a particular level of accuracy, because yeah, I kind of mentioned that exponentials, if you have tiny mistakes with accuracy, exponentials will blow those up really quickly. So you want to be fairly accurate with them. So yeah, so I got x equals 8.07. I think like after that it was another 0, so that's pretty accurate. I'm just going to check my answer here. If I do e to the 8.07, and so remember that e button should be buried behind the ln button. So e to the 8.07, I get 3,197, right? Very close to 3,200. A little bit of error, and that is going to happen. If I wanted closer, I would just keep more decimal places. But that's pretty much the x that I wanted for that. So that looks good for x. Yeah, so that would be the gist. Yeah, so from this point forward, you're going to see these lns and logs without anything written underneath them. So you just kind of got to know that one's base 10 and one is base e.